You know, usually when we think about a fortress, we picture something incredibly static.
Right, exactly.
Like we imagine massive stone walls, a heavy iron gate, maybe a deep moat, if you're feeling dramatic.
Yeah, the classic medieval setup.
Right, and it's considered strong precisely because it never moves. It just sits there, daring something to try and break it.
Which totally makes sense. The physical world really rewards that kind of rigidity. But the moment you step into the world of modern enterprise data storage, that physical fortress metaphor completely falls apart.
It really does.
Yeah, because we are looking at a defensive landscape that is entirely fluid. The digital fortress has to be constantly moving, self-healing, and actively learning, all while remaining completely impenetrable.
It's a total paradigm shift.
It really is. It changes how we think about security and infrastructure from the ground up.
Well, welcome to this deep dive. The digital fortress has to be dynamic to survive. And if you are gearing up to pass the NS0-165 exam, understanding how to build and defend that fluid fortress is exactly what will get you your certification.
Absolutely.
Our mission today is highly specific. We are cracking open the study materials to dissect the foundational architecture of how data is managed, protected, and, optimized.
But before we get into the technical weeds, let's establish the basic logistics you will face.
Yeah, that's a good idea. Setting the stage.
Right. So the material lays out a 90-minute test environment. You'll be tackling approximately 60 items, which are going to be a mix of formats.
With multiple choice and stuff.
Exactly. Multiple choice, matching, and some drag and drop formats, too. You need a 64% to pass, and the current fee sits at $150 US.
So 90 minutes for 60 questions. That's fairly quick.
Yeah, time management is going to be critical, meaning you cannot afford to second-guess the underlying concepts.
Okay, let's unpack this. Rather than just reading you a list of facts or throwing flashcards at you, we're going to do something much more practical.
I like practical.
Right. We have pulled 10 specific practice questions directly from the source material. We are going to read every question stem, analyze every single option provided, and uncover the actual problem-solving logic.
Because when you truly understand the why behind the technology, the correct answer usually just reveals itself.
Exactly. So let's dive into the first piece of the physical plumbing. The first question stem asks, which storage platform is specifically architected to provide symmetric active paths for block-level protocols by default?
Okay, a classic architecture question.
Yeah, and it gives us 4 options. A, fabric-attached storage. B, ONTAP select. C, all-flash fabric-attached storage. And D, all-flash SAN array.
To solve this, we have to look at option D, the all-flash SAN array, or AFSA.
Okay, so D is the winner.
Right. And what's fascinating here is the physical mechanism behind that phrase, symmetric active.
Break that down for us.
So in a traditional setup, you might have multiple controllers, right? But one is doing the heavy lifting for a specific data volume, while the other acts as a backup or handles different traffic.
Kind of like a primary and a standby.
Exactly. But the AFSA is explicitly designed so that both controllers in the system actively handle input and output operations for the exact same logical unit number simultaneously.
Oh, wow. Okay, so it makes me think of a busy grocery store.
Okay, I like where this is going.
Like a traditional single-path setup is like having one cashier scanning your groceries. It works, but there is an undeniable bottleneck.
Right, you're waiting in line.
Yeah, but the symmetric active architecture of AFSA is like having 2 cashiers simultaneously checking out the exact same customer's groceries out of the same cart.
That is a perfect visual. It balances the load perfectly and minimizes latency.
Which is crucial, right?
Highly crucial for mission-critical storage area networks using protocols like Fiber Channel, ISCSI, and NVMe.
So that parallel processing is the key.
Yeah. And it is also why we can instantly eliminate options A, B, and C.
Because they aren't built for that by default.
Exactly. I mean, fabric-attached storage, ONTAP Select, and all-flash fabric-attached storage are incredibly powerful platforms. But the exam question hinges on the phrase, architected by default.
Ah, the exact wording matters.
It always does. The AFSA is the platform uniquely built from the ground up to default to these symmetric active block paths.
Got it. So we have established this blazing fast, balanced hardware traffic, but what happens when you have multiple competing departments?
Like internal departments sharing the system.
Yeah, say HR and finance are running on that exact same high-speed physical hardware. How do we keep them from stepping on each other's toes?
That is exactly what the next question tackles head on.
Awesome. The STEM reads, what provides complete management and data isolation for different tenants or departments sharing the same physical cluster?
And the options.
The options are A, virtual local area network, B, storage virtual machine, C, logical storage tier, and D, physical aggregate.
Okay, so the mechanism you were looking for here is option B, the storage virtual machine.
Or SVM.
Right. Yep. SVM. An SVM acts as a secure logical container within the operating system. It allows multiple tenants to share the exact same physical storage cluster while remaining entirely invisible to one another.
Invisible? Really?
Completely. Each SVM gets its own dedicated storage resources, its own network configuration, its own distinct security settings, and even its own management interface.
It is essentially like turning a massive single-family mansion into a secure apartment building.
Yes, exactly.
Like everyone shares the same foundation and the same roof, but everyone has their own locked door and their own utility meters.
That's a great analogy. And if you look at the incorrect options, the traps become pretty obvious.
Walk us through them. Option A was virtual local area network.
Right. A VLAN is strictly a networking concept. It segregates traffic, sure, but it doesn't isolate storage management.
Makes sense. What about C and D, logical storage tier and physical aggregate?
Those are just underlying storage components. None of them provide the complete top-to-bottom management and data isolation that the text attributes to the SVM.
So secure multi-tenancy requires isolating every layer of the stack.
Precisely. And only the SVM provides that unified container. Now, we need to look at how these virtual containers handle physical hardware failures.
Without the tenant ever noticing, right?
Exactly.
That brings us to a pair of scenarios I like to call the high availability duo.
Oh, I like that.
The first STEM asks, which logical component allows a network address to migrate between physical ports during a hardware failure to maintain client connectivity?
And the choices.
We're given options A, logical interface, B, broadcast domain, C, failover group, and D, subnet mask.
We find our answer in option A, the logical interface, or LIF.
Okay, LIF.
Yeah. We basically need to detach our thinking from the idea that an IP address is permanently burned into a physical piece of metal.
Right, because normally you think of an IP tied to a specific network card.
Exactly. But an LE is a virtual network endpoint. So if the physical port it is currently using suddenly burns out, or if an administrator takes that node offline, the LEF actually detaches its IP address and its MAC address.
Wait, it just detaches?
Yep, detaches, floats across the system, and instantly re-registers on a surviving port.
That is wild. So the client application on the other end is completely unaware that a piece of hardware just died.
Because the IP address it is talking to never changed. It just magically moved.
Wow. And that mobility instantly disqualifies options B, C, and D.
It does. A broadcast domain, a failover group, and a subnet MAC are static network boundaries or groupings.
They just sit there.
Right. They simply do not possess the ability to pick up an identity and migrate across a cluster.
So that virtual mobility is the cornerstone of non-disruptive operations. And it pairs perfectly with the physical side of hardware maintenance, which the next question explores.
Let's hear it.
Okay, let's read that STEM. During a planned maintenance event, which feature allows storage services to be moved to a partner node without disrupting client access?
Okay, maintenance event.
The options are A, storage failover, B, volume move, C, aggregate relocation, and D, cluster peering.
The solution here is option A, storage failover, or SFO.
SFO, got it.
In this high availability architecture, nodes operate in pairs. So say you need to upgrade the firmware on node 1. It has to physically reboot, right?
You can't avoid a reboot for firmware.
Exactly.
Yeah.
But before it does, storage failover allows node 2 to temporarily take over all the storage resources and network identities of node 1.
So node 2 is doing double duty.
Yes. Node 2 serves data for both machines. Client access remains completely uninterrupted, and once node 1 wakes back up, the resources are seamlessly handed back.
Okay, let me push back here for a second.
Sure.
Because this sounds incredibly complex. I mean, why go through all the trouble of setting up virtual interfaces that float around and partner nodes that have to shoulder double the workload during a reboot?
It does sound like a lot of work.
Right. Why not just buy more standalone hardware servers and keep them completely separate so a failure is contained?
Well, if we connect this to the bigger picture laid out in the exam materials, buying separate standalone hardware creates isolated islands of data.
Islands of data?
Yeah. When an island experiences a hardware failure, everyone relying on that island experiences total downtime.
Ah, and downtime is the enemy.
Exactly. The entire philosophy of this architecture is continuous availability. The ecosystem is designed to absorb hardware failures and mask maintenance events so that the end user never experiences a blink in service.
So you are building a resilient fabric, not just racking and stacking hard drives.
That is the perfect way to put it.
Let's look at the incorrect options for that maintenance scenario. Volume move, aggregate relocation, and cloud repairing.
Right. While they move data or connect different clusters together in various ways, they do not describe this specific temporary partner node takeover function designed to mask physical reboots.
Moving data permanently is very different from temporarily assuming a partner's identity.
Completely different. Now let's examine the speed at which all this data travels across the network.
Good transition. The next question stem reads, compared to traditional ISCSI, what is a primary advantage of implementing NVMe over TCP?
A classic protocol showdown.
The options are A, support for legacy hardware controllers, B, simplified zoning and cabling requirements, C, higher throughput and lower processing overhead, and D, built-in integration with older network switches.
Option C is the correct answer here. NVMe over TCP offers remarkably higher throughput and lower processing overhead.
Why is that?
Well, to understand why, we have to look at the protocols themselves. Traditional ISCSI is based on standard SCSI commands, which were originally designed for spinning disk drives.
Oh, the old physical platters.
Yeah, it is a heavy serialized protocol. NVMe, on the other hand, was built from scratch specifically for the massive parallel processing capabilities of flash memory.
So by running NVMe over standard TCP/IP networks, you are basically taking a lightweight, hyperfast protocol and pushing it through the standard Ethernet plumbing you already own.
Exactly. You strip away the legacy protocol overhead, allowing the CPU to process thousands of commands in parallel rather than waiting in a single file line.
Which means options A, B, and D are deliberate traps.
Oh, 100%.
They try to trick the test taker into thinking NVMe over TCP is like a backward compatibility play, referencing legacy controllers, older switches, or cabling simplification.
Yeah, the text is clear. The core advantage of NVMe is strictly about modern performance metrics, getting lower latency and higher throughput over familiar infrastructure.
Getting that incredible low latency speed is great for performance, but it introduces a terrifying reality.
It really does.
If your system is processing and moving data that fast, a localized disaster will wipe out that data just as quickly. That is where we have to shift our focus from pure performance to pure survival.
Because a dynamic fortress still needs incredibly robust data protection. Speed is a massive liability if the data isn't secured instantly.
So true. Let's look at the first protection scenario in the study guide. The STEM asks, which SnapMirror relationship type ensures a zero recovery point objective by acknowledging writes only after they are secured on both clusters?
Zero recovery point objective is the key phrase there.
The options are A, asynchronous replication, B, extended data protection, C, version flexible replication, and D, synchronous replication.
The mechanism described is option D, synchronous replication.
Synchronous, okay.
Yeah. The critical phrase in the question stem is acknowledging writes only after. This is a real-time guarantee.
How does that work in practice?
So when a host sends a piece of data to the primary storage system, the primary system does not immediately tell the host, write successful.
It makes it wait.
Exactly. It holds that acknowledgement, transmits the data across the network to the secondary disaster recovery site, waits for the secondary site to confirm it has written the data to disk, and only then does the primary system acknowledge the original host.
Wow. So both systems contain perfectly identical data at the exact same millisecond?
Yes. So if a fire destroys the primary data center, exactly zero data is lost.
That is the definition of a zero recovery point objective.
You got it. And that strict waiting mechanism is why options A, B, and C fail the test.
Because they don't wait.
Right. Asynchronous replication, extended protection, and version flexible replication are fantastic for routine backups. But they acknowledge the host immediately and send the backup later.
So there's a gap.
Yeah, a time gap. They cannot guarantee that zero data loss required for Tier 1 mission-critical applications.
Gotcha. Moving from natural disasters to human threats, we have to address regulatory compliance and, tampering.
A huge issue right now.
Definitely. The next stem reads, which technology provides worm protection for data to ensure it cannot be modified or deleted during a retention period?
Worm protection.
We have options A, SnapMirror ActiveSync, B, SnapVault Archive, C, SnapLock, and D, SnapRestore.
Option C, SnapLock, provides the write once, read many, or worm capability.
Write once, read many.
Exactly. This is specifically engineered to meet strict regulatory compliance mandates, like those found in healthcare or financial sectors, where data immutability is literally legally required.
I always compare SnapLock to pouring wet cement.
Oh, that's good.
You can write the data into the system, but once that cement dries, it is permanently set.
Perfect analogy.
It cannot be altered, it cannot be encrypted by ransomware, and it cannot be deleted by an administrator until the predefined retention clock officially runs out.
It removes human error and malicious intent from the equation entirely.
Which is huge.
Yeah. And when we look at the other options, SnapMirror ActiveSync, SnapVault, and SnapRestore, we're looking at standard synchronization or backup tools.
Right.
A standard backup can be manually deleted by an administrator with the right credentials. SnapLock overrides those credentials to enforce the retention period at the system level.
Here's where it gets really interesting.
Okay.
We cannot talk about modern data defense without addressing the elephant in the room, ransomware.
Unavoidable topic.
Right. The next STEM asks, what is the primary purpose of the learning mode within the autonomous ransomware protection feature?
Learning mode.
The options are A, to establish a baseline of normal file system activity, B, to automatically delete suspicious snapshot copies, C, to encrypt volumes currently under active attack, and D, to upgrade the storage operating system automatically.
The correct mechanism is option A.
Establishing a baseline.
Right. The primary purpose of learning mode in autonomous ransomware protection, or ARP, is to establish a baseline of normal file system activity. You cannot possibly identify abnormal behavior if you do not have a mathematical definition of what normal looks like for your specific environment.
But wait, let me ask a clarifying question about this.
Sure. Go ahead.
If the system is actively learning, what happens if a slow, stealthy ransomware attack is already underway during that learning phase? Won't the system just learn that the malicious encryption is part of the normal baseline?
That is a critical concern and a very common question. But ARP learning mode is far more sophisticated than just measuring the speed of file writes.
How so?
It deeply analyzes file entropy, meaning how randomized the data within the files is becoming, as well as observing changes to file extensions and access patterns.
Oh, so it's looking at the actual behavior of the file.
Yes. It uses those complex heuristics to define legitimate user activity versus malicious encryption algorithms. It is a purely observational, analytical phase.
Which perfectly explains why options B, C, and D are entirely wrong.
Exactly.
Learning mode does not automatically delete snapshots, it does not encrypt volumes, and it certainly doesn't upgrade the OS. Those are active mitigation or maintenance tasks.
Right. Learning mode is strictly about gathering intelligence.
Okay, so we've built the plumbing and we've heavily fortified the walls. Let's zoom out to the big picture.
Sounds good.
Now that everything is running smoothly and is heavily protected, how do administrators efficiently store all this data without going bankrupt? And how do they monitor the health of this sprawling ecosystem?
Because efficiency and overarching visibility eventually become just as critical as raw speed and security, you have to optimize the footprint.
Let's look at the next scenario. The STEM reads, in a fabric pool configuration, which storage type is typically used for the cloud tier?
Fabric pool.
The options are A, high-performance solid-state drives, B, high-capacity serial-attached SCSI drives, C, object storage from a public or private provider, and D, fiber channel connected storage arrays.
The answer is option C, object storage from a public or private provider.
Okay, object storage.
Yeah. Fabric pool is an automated tiering technology. Every organization generates data that is heavily used for a few weeks, right? And then it's rarely touched again.
Oh yeah, tons of it.
So Fabric Pool keeps that hot, active data on your expensive, high-performance local storage. But as data cools down and becomes inactive, it automatically moves those specific blocks to a lower-cost cloud tier.
It's basically like cleaning out your expensive downtown apartment and moving the holiday decorations you only use once a year into a cheaper storage unit out in the suburbs. And the system handles the moving truck automatically.
Exactly. It optimizes your capital expenditure. And the text explicitly states this cost-efficient cloud tier utilizes object storage.
Which makes identifying the wrong answers pretty straightforward.
Right. High-performance SSDs, high-capacity SAS drives, and fiber channel connected arrays options A, B, and D all represent local, traditional, or high-performance hardware.
Using them would completely violate the fundamental definition of a low-cost, infinitely scalable cloud tier.
Exactly. It completely misses the point of Fabric Pool.
Let's bring it all home with our final practice question, which deals with ecosystem visibility.
The big picture view.
Right. The STEM asks, which management tool provides AI-driven health scores and proactive recommendations based on community-wide data analytics?
Okay.
We have options A, Active IQ Unified Manager, B, System Manager, C, Cloud Insights, and D, On-Command Workflow Automation.
The specific tool described is option A, Active IQ Unified Manager.
Okay.
This platform provides deep visibility into performance, capacity, and system health. But the key differentiator highlighted in the exam text is its use of AI-driven analytics combined with community-wide telemetry data.
Community-wide telemetry, so it isn't just looking at your localized hardware.
Not at all.
Yeah.
It is continuously learning from the telemetry data of thousands of other systems across the globe.
Wow. So if a specific firmware bug causes an issue in a data center in Tokyo, the AI learns from it and proactively warns your system in New York to apply a fix before the bug ever hits your workload.
Yes. It shifts infrastructure management from being reactive to being entirely proactive.
That is incredibly powerful.
It is. And options B, C, and D, System Manager, Cloud Insights, and On-Command Workflow Automation are all highly useful operational tools. But Active IQ Unified Manager is uniquely identified in the study materials by that specific combination of community-wide AI and proactive health scoring.
Thank you so much for taking this deep dive with us today into the NS0-165 materials. Best of luck with your studying, and we will see you next time.